Alright, so we're going to do our introduction to special relativity here. And this introduction is going to be on different transformations. Up until this point, we've worked in what are called the Galilean transformations, and these were from Galileo, obviously. And what these did was tell you if you had, a couple of different coordinate systems, which we will start calling frames of reference, and we label this one as x and like this is y. You could have another coordinate system, or really any other coordinate systems. They could be rotated like this, x and y, or anything like that. And we're going to look at a simple example here, is that they can be rotated, they can be flipped, they can be turned over, they can be whatever. But let's look at the simple example where we have this coordinate system and then we have another identical coordinate system lined up with it at first. But this second coordinate system, we'll call it the prime coordinate system, x prime, y prime. This coordinate system itself is actually moving to the right at some speed v. And so if we knew the location of something in the xy coordinate system, we want to know what's its location in the x prime, y prime coordinate system. And so if we had some object that was sitting, let's say just sitting right here, and we in the xy coordinate system said, oh, that's whatever this distance over is here, this x value there, could be 3 meters or something. What would it be in this other coordinate system as it moved to the right? Well, it would start off as something positive if these were lined up right when we first started looking, and it would be also whatever this was, 3 meters or something like that. But as time went on and this coordinate system moved to the right, this thing's location would appear to that coordinate system to be moving to the left, so its position would change. It would go from 3 to 2 to 1 to 0, and then off into negatives. And it turns out the way you do this is through the Galilean transformations that look like this. X prime, so the coordinate in the prime set, is equal to x minus v times t. And this should make sense to you because it's whatever the coordinate is, and then at time t equals 0, this would be 0, and it would just be x prime equals x. And that's right at the very beginning when they're lined up. But as time goes on, Vt gets bigger and bigger, so we're subtracting more and more off, and so this thing's apparent position to x prime coordinate system, it starts reducing, goes to 0, and then becomes negative as Vt gets bigger and bigger. All right, y prime in this situation would just be y, but you could have a minus Vt here if it was this was like v sub x and this was v sub y. Z in this situation is unchanged, and then time is also unchanged. And when we have something that's unchanged, that is always unchanged, we call it an invariant quantity. And Newton and everything, they said that time and space were invariant. You could change your coordinate system, but they ultimately stayed the same. And this was fine, and it worked really well for a long time. We got all the physics we've done up until this point based on this. It'll get you to the moon, basically. But the Michelson-Morley experiment came along where they tried to measure the speed of light. And the idea was that since light was a wave, it must be traveling through some sort of medium, because all physical waves do this. And so this medium, they called it the ether. So as Earth, let's say this was Earth, was traveling through space in this direction, if we had light being shot out and we measured the light speed in the direction that we were going, then we would move along with it. And if we measured the light speed in the direction we were coming from, we would be moving away from it. And so we would get a greater speed measuring the direction we came from, and a smaller speed in the direction we are headed, kind of like the waves coming off a boat. If you look at the waves coming off a boat, the waves out in front, they aren't moving away from you as fast, so they stay bunched up and close and they don't get that far away from you. But the waves coming off the back of the boat get way spread out because they seem like they're going faster compared to you, because you're moving this way and they're moving that way, and your velocities add up, and the waves do that. So they expected light to do the same thing. Only problem was it didn't. It didn't do that. No matter what direction they pointed the light, no matter what they did, every time they measured the speed of light in a vacuum, they found, and that's an important part in a vacuum because it does slow down inside mediums. We learned that with index of refraction. But the speed of light in a vacuum, they found it wasn't changing. And every time they measured, they got 8 times 10. They got 3 times 10 to the 8th. I'm putting the wrong number there. I'm sorry. My brain stopped working. They got 3 times 10 to the 8th meters per second. I knew there was an 8 in there. 3 times 10 to the 8th meters per second. So that's really, really fast. But they couldn't get it to change. They couldn't get any variation from it. It was always this. And so no one knew how to explain this. But then Einstein came along, and he used what were known as the Lorentz transformations. Okay? And he postulated that, like Newton, he thought that the laws of physics would be the same for all inertial frames. Okay? Inertial frames, this is basically any non-accelerating coordinate system. Non-accelerating coordinate system or reference frame. So any non-accelerating coordinate system, he said that these Lorentz transformations would hold true for any inertial thing, and all the laws of physics would be the same for them, and that included keeping the speed of light the same. So he used these things, and these Lorentz transformations, they look a little different than the Galilean ones, and they are x prime equals gamma. I'll write what gamma is in just a moment. X minus vt. So pretty similar. Assuming we're not moving in the y direction, these will stay the same. Just writing them for completeness. And then here's the interesting part, time. Time looks very different. We once again have this gamma, but then we have t minus vx over speed of light squared. And what he said is this speed of light, we're going to denote it with a c here, standing for the universal constant. No matter what you're doing, it doesn't change. And so since it wasn't changing, and since the laws of physics had to be the same for everybody, we actually needed these coordinate system transformations to make it all work. Okay, so these are very important. And then of course what gamma is. Gamma, little scaling factors, 1 over the square root of 1 minus the speed of your object over c squared. So 1 over the square root of 1 minus v squared over c squared is gamma. And these are your Lorentz transformations. And they're the foundation of pretty much everything we're going to be doing in this whole section, this whole topic. It comes from these. If you ever want to invert them, so this is going from the prime coordinate to the you have the unprime coordinate, what would be like the stationary coordinate. You want to go to the prime one, you do this. If you want to inverse these, say you have all the prime information and you want the unprime, well, essentially, if you're in the prime coordinate and you look at the unprime coordinate, instead of considering yourself moving to the right, you would see the unprime coordinate moving to the left. And then that would just make every v a negative of what it is, and you would get these. X equals gamma x prime plus vt. So these are the inverse ones. Y and z stay the same, and then t is gamma t prime plus vx over c squared. So if you ever have to reverse them, this is what you would do. This still equals y prime. Z still equals z prime. This would be the inverse version of them. Gamma would stay the same for that, but this would be the inverse versions of that coordinate system transformation, okay, of these Lorentz transformations. And so ultimately, this will start to have a lot of fun, neat things that fall out of it. But you have to keep in mind that we have to have the laws of physics be the same for everybody. So there has to be a reason why we all measure the speed of light to be exactly this, no matter how you're moving. And it actually turns out it's all built into here. And in the next few videos, we'll try going through and deriving a few things that go along with this, and not just a few things along. So we'll use this for quite a lot of things, and we'll also do some diagramming and things like that with this to understand this a little better. But right here is pretty much everything you would need to solve these problems. And you throw these in with these postulates that the laws of physics have to say the same, and everything works out nicely. But it has some weird consequences that go along with it. Okay, so a couple things I forgot to mention. Up here, with the Galilean transformations, the speed of light was not a constant. It would have been invariant. That means that, like, if you were driving along in your car, right, say you're in a car, and the car is going at 60 miles per hour, and you can throw a baseball out in front of you, so you stand up out of the sunroof or something, and you throw this baseball, and you throw the baseball at 60 miles per hour, then for someone standing on the side of the road watching that baseball go by, how fast would they see that baseball go? They'd see it go the 60 that you threw it, right? Plus the 60 the car was already going. And so for them, their little device here, if they're reading on a radar, would read 120 miles per hour. And that's what you would expect. It's this thing. And so according to these equations, that's what would happen. Now, if we replace that ball, right? We don't have a ball anymore. Instead, what we have is like a laser light or something, right? And you're in a car that's driving 60 miles an hour, and you shine your laser light in front of you, and it would be, of course, 3 times 10 to the 8th meters per second from your perspective in the car, right? Whatever that happens to be. It'd be way bigger than that, but 3 times 10 to the 8th meters per second. And then someone standing on the side, they clocked it. According to Newton, what would they get? They would get 3 times 10 to the 8th meters per second plus the 60 miles per hour. Of course, you'd have to convert your units, but this is what they should see. They should see something a little faster than the speed of light. But according to the Michelson-Morley experiment, we weren't able to change that. And so if you do this same thing again, you do this same experiment again, it turns out this guy on the side of the road, if you do this, he doesn't measure 3 times 10 to the 8th plus 60. He doesn't get a little faster than the speed of light. He gets exactly the speed of light. And if you use some radar detector or whatever, and you measured this speed of light as well from your car while you were moving at 60 miles per hour, you would also get this 3 times 10 to the 8th. So no matter how you're moving, what you're doing, everybody measures this speed of light exactly the same. And so this over here actually has that built into it and helps us figure out that why we both end up measuring the same speed for the speed of light no matter what happens. All right, so we'll get some more into that into the next video, and I think that's all for the introduction.